In previous videos, we've looked at some number systems where primes inside of the integers are perhaps no longer prime. Or maybe the notion of primeness kind of falls apart altogether. Well, today I'd like to look at another extension of the integers where this kind of thing occurs. So let's recall some of the stuff that we've seen before, or maybe some of the stuff that is related to what we'll look at today a little bit more deeply. So let's first consider this set called the Gaussian integers. So that is z adjoint I. So in other words, it's complex numbers where the real part is an integer and the imaginary part is also an integer. So everything of the form a plus bi, where a and b are integers. Now, I'd like to observe that we can write 2 as 1 plus I times 1 minus I. So that means that this number 2 is no longer prime inside of the Gaussian integers. Likewise, we can write 5 as 2 plus I times 2 minus I. So 5 is no longer prime. We can write 13 as 3 plus 2i times 3 minus 2i. So 13 is no longer prime. In fact, while we won't prove this, this kind of generalizes, or maybe the general result here, I should say, is that if P is congruent to 1 mod 4, I guess it's a prime that's 2 mod 4 or 1 mod 4, but there's only one prime that's 2 mod 4, and that's 2, and so we have that here. So anyway, if a prime P is congruent to 1 mod 4, then that means it's possible to write P as the sum of squares. In other words, in the form a squared plus b squared. But once we get it in that form, we can rewrite it as a plus bi times a minus bi, and then we've factored it inside of these Gaussian integers. So in other words, if you've got a prime that's 1 mod 4, it's no longer a prime in the Gaussian integers. Now, here are some quick other examples. Let's say we are inside of z adjoined the square root of minus 5. So that's just going to be everything of the form a plus b root minus 5, where a and b are integers. Now here, the notion of primeness kind of falls apart in another way. And I wouldn't say it falls apart for everything, but it falls apart for certain numbers that are primes inside of the integers. Observe that we can write 6 as 2 times 3. But we can also write it as 1 plus root negative 5 times 1 minus root negative 5. And why this breaks the notion of primes is that this factorization of 6 is no longer unique. And if you recall from the fundamental theorem of arithmetic, we kind of have this uniqueness of factorization into primes. But if we look inside of this set, we no longer have unique factorization. Now, just as one other example, if we take z adjoining the square root of 2, let's observe that 7 is not prime. 7 can be written as 1 plus 2 root 2 times minus 1 plus 2 root 2. And in fact, I think you could play this same kind of game, but here you would try to find primes of what form? Well, I think they're going to be primes of the form a minus 2 times b squared, or a squared minus 2 times b squared. And if you can find a prime of that form, then you can factor it within this extension of the integers. Okay, cool. So now what I'd like to look at is something called the Lipschitz quaternions. So what are those? So those are going to be a certain integral form of the quaternions. And there are in fact 2 different integral forms of the quaternions. Here we're looking at these Lipschitz quaternions. There are also Hurwitz quaternions if you want to look into those on your own. So they're everything of the form a plus bi plus cj plus dk, where a, b, c, and d are integers. And then I, j, and k are the imaginary units inside of the quaternions. So that means that I squared is the same as j squared is the same thing as k squared, which is minus 1. And then the multiplication of I, j, and k follow this pattern where I times j is equal to k, but j times k, or j times I, is equal to negative k. So in other words, if you want to find the product of 2 of these units, I, j, or k, what you do is either follow the arrows or reverse the arrows. And if you follow the arrows with your product, you get a plus sign. And if you go against the arrows, you get a minus sign. So in other words, I times k, since it's reversed the arrows, is minus j. Now I'd like to observe the following, and that is that there's a notion of a conjugate within these quaternions that allows you to multiply a quaternion by some sort of obvious thing connected to it that will give you a positive real number, or I should say a non-negative real number. So let's observe the following. If we take a plus bi plus cj plus dk, and you multiply it into a minus bi minus cj minus dk, what are we going to get? Well, maybe I won't do the whole calculation, but let's observe that we get a times a, which is a squared. We get bi times negative bi, but that's going to be b squared because we get negative I squared, which is negative negative 1, so we get plus b squared. We similarly get c squared and d squared. So that's the real part. And now let's look at what the coefficient of I would be. So here I'll put a big parentheses here, and then we'll put inside those parentheses what the coefficient of I is. So let's observe we're going to have a times b, or really a times negative b. So that's going to be minus ab. And then here we'll have b times a. So that'll be plus ab. So let's observe that those are going to kind of obviously cancel. But do we get anything else? Well, yes, we do. Let's observe that we get cj times dk, but since j times k is I, that's going to give us a negative c times d. And then we also get dk times cj, or minus cj, I should say, but that's going to be cd and then k times j. Well, that's going to be equal to negative I. So in the end, you get a plus sign there. So here we get plus CD. But the important thing here is that this zeroes out. Notice that everything is attached to its negative in some way. And this will be true for the JK components as well. So here we get this number, a squared plus b squared plus c squared plus d squared. But this gives us a motivation for a way to factor inside of these Lipschitz quaternions, or in a way that maybe we couldn't factor inside of the normal integers. So let's notice the following. So we still have 2 is equal to 1 plus I times 1 minus I, because if you're just adding in the I, it's just like the complex numbers. But notice that's going to be the same thing as 1 plus j times 1 minus j, and 1 plus k times 1 minus k. So in fact, we can factor 2 these ways, but that factorization is not unique. Now, what about 3? So let's observe that we can factor 3 as, well, actually, let's write down this fact that 3 is equal to 1 squared plus 1 squared plus 1 squared. And then read this equation that we've just built in reverse to perform this factorization. So in other words, a, b, and c are 1 and d is 0. So this gives us something like this: 1 plus I plus j, 1 minus I minus j. But of course, we really just have to choose any 2 of these 3 imaginary units and we get the same kind of thing. So this is the same thing as 1 plus I plus k and 1 minus I minus k. So there we factored 3 2 different ways, meaning 3 is no longer a quote-unquote prime. And I would say that these things are also not primes because we don't get this unique factorization, which means we should probably introduce some sort of word for what's happening here. We're not factoring into primes, we're factoring into so-called irreducibles. And when I say an irreducible, I mean something that just can't be factored anymore. And I'm not going to check this super carefully, but like 1 plus I can't be factored anymore into like reasonably smaller pieces. Then this 1 plus I plus j also can't be reasonably factored into smaller pieces. Now, there's one more way to factor 3. I'll let you write that down. So now let's look at some others. So we could have 5 as 2 plus I times 2 minus I. Of course, that's also going to be equal to 2 plus j times 2 minus j, and 2 plus k times 2 minus k. Perhaps other things as well if we just like put together the J's and K's carefully. Actually, maybe not. I think this is the only 3 ways. Now, what about 7? So let's observe that we can write 7 as, well, it's going to be 2 squared plus 1 squared plus 1 squared plus 1 squared. And then using this product in reverse to factor, that's going to be 2 plus I plus j plus k. And then 2 minus I minus j minus k. So there we have that. And then, well, we actually might think that this is unique, but it's not really, because we could switch some signs and get the same kind of result. Notice we could have, for instance, 2 minus I plus j minus k, and then 2 plus I minus j plus k. As long as the signs are different in each of these, this whole thing works out. So I think maybe what we're motivating here is it looks like every prime can be factored in these Lipschitz quaternions. Maybe we could do some more examples to really convince ourselves of that, but instead, let's maybe provide a proof that in fact, every prime can be factored in this Lipschitz quaternions, which means none of the normal primes are primes anymore. All right, so now for the main result, and that is that none of our normal primes are prime in L. But I'm actually going to cross out this word prime here, because since in L, this Lipschitz quaternions, there doesn't seem to be unique factorization, perhaps we shouldn't use the prime here, or the word prime here. So what I'll do is use the word irreducible here, which is looser than prime in the first place. So none of our normal primes are irreducible in L. And we're going to use a standard proof that every prime can be written as the sum of 4 squares. And then we'll take that sum of 4 squares and then factor it in our Lipschitz quaternions. Okay, so let's get to it. So let's suppose P is an odd prime. So we're going to take an odd prime because the prime 2 is already taken care of from our observation when we were like kind of playing a game with the factorization in the first place. Okay, and now let's make the following claim, and that is that there exists a number n less than p such that n times p is equal to a squared plus b squared plus c squared plus d squared with a, b, c, and d integers. So the first thing to do is prove that we can get a multiple of p written as the sum of 4 squares. And then what we'll do is show that we can push that multiple of p down just to p itself. Okay, so this isn't so bad. Let's consider 2 sets of numbers. So our first set I'll call A, and that's going to be 0 squared, 1 squared, 2 squared, all the way up to p minus 1 over 2 squared. So that's going to be a set of integers. Since p is an odd prime, p minus 1 is even, divided by 2, that's still an integer. Okay, and now I'd like to also observe that the number of elements in A is p plus 1 over 2, because we're starting counting at 0. Now we'll next look at this set B, which is going to be related. It's actually going to be minus 1 minus A, as A runs through A. So it's just going to be these things shifted in a certain way. Well, I guess negated and then shifted. But since we're building B out of the elements of A, that means that the number of elements in B is also p plus 1 over 2. So now what I want to do is make an observation, and that is that A intersect B is empty. I think it's pretty clear that these 2 sets don't share any elements. And since the intersection is empty, that means that the number of elements in A union B is simply equal to the number of elements in A plus the number of elements in B. But if you add those 2 things up, you get p plus 1. But p plus 1 is bigger than p, so that means by the pigeonhole principle, we should be able to find an element of A and an element of B that are congruent mod p. So in other words, there exists something that I'll call x squared inside of a. I'm going to write it as x squared because let's observe that everything inside of a is a square, and something that I'll call minus 1 minus y squared in b. I'm going to write it like that because notice by construction everything in b looks like that, such that we have x squared congruent to minus 1 minus y squared modulo p. So we've got something like that. But now let's observe we can move some things around here, and we get that x squared plus y squared plus 1 is congruent to 0 modulo p. But that means that x squared plus y squared plus 1 squared is equal to n times p for some number n, which I guess is going to be a natural number just given that the left-hand side is positive. Okay, nice. But now I'd like to observe that we can get some sort of estimated range for n. Let's notice that n times p is going to be equal to x squared plus y squared plus 1. But notice that that's going to be less than p minus 1 over 2 squared plus p minus 1 over 2 squared plus 1. Just given that the size of x and y is less than or equal to p minus 1 over 2 squared by construction. But that's going to be less than p squared just by calculation. But if np is less than p squared, that means that n is less than p. But check it out. That's what we wanted to do here. We wanted this claim where there existed an n less than p so that np was the sum of 4 squares. Well, we actually did a little bit better. We found np was the sum of 3 squares. X squared, y squared, and 1 squared. And I guess our fourth square would be 0 squared because we allow 0 to be a square in this setup. Okay, nice. So now what we'll do is take a number m, and let's see, this number m has got to be a natural number such that m is the smallest, such that m times p can be written as the form a squared plus b squared plus c squared plus d squared with a, b, c, and d being integers. And I guess it's kind of obvious what we want to show is that m is equal to 1. In other words, the smallest way that we can build this is, in fact, just with the prime itself. Okay, so this is going to split into two cases. So the first case is fairly quick. So, and that is what happens if m is even. Well, notice if m is even, the right-hand side of this equation is even, which means the left-hand side of this equation is even. But if the left-hand side of this equation is even, that means 2 of these are even and 2 of these are odd. Or they're all even and they're all odd. So, but either way you look at that, we can pair these things off into things that are congruent mod 2. So if they're all even, then A and B are congruent mod 2 and C and D are congruent mod 2. If they're all odd, well, the same thing. If 2 are even and 2 are odd, we can rename these so that A and B are both even, for instance, and C and D are both odd. So just putting that all together, we have A is congruent to B mod 2 and C is congruent to D mod 2. But what does that mean? That means that a minus b over 2 and a plus b over 2 are integers. In other words, this equation right here, a minus b over 2 squared plus a plus b over 2 squared plus c minus d over 2 squared plus c plus d over 2 squared is an expression with only integers. Notice a minus b over 2 is an integer because of this congruence, and similar for the other ones. But then if we do this calculation, we get exactly m over 2 times p. So I'll let you expand all that out and see that you do get that expression. But notice that contradicts the minimality of our number m, because we've expressed m over 2 times p as a sum of squares. But we said that m was the smallest one where that was possible. So that means that m must be odd, because if it's even, we have a contradiction. Okay, so let's see what goes wrong if m is odd. Thanks for sticking around this long into the video. If you're enjoying the video, make sure and give a thumbs up. And if you're not yet subscribed, consider subscribing. It really helps out. Okay, so what have we done so far? Well, we took p to be an odd prime and m to be the smallest natural number, so that m times p could be expressed as the sum of 4 squares. Then, in the case that m is even, we reached a contradiction, which means that this minimum value of m cannot be an even number. Now let's look at the case when m is odd. So here's what we're going to do here. Let's pick some numbers. We'll call them x, y, z, and w, and they're going to be between minus m over 2 and plus m over 2. Notice that these are half integers, so it can't be equal to either of those, but it can be in between those, so that we have a is congruent to x mod m. We have b is congruent to y mod m. We have c is congruent to z mod m. And then finally we have d is congruent to w mod m. And you might say, well, why is this possible? Well, if you look at the number of integers between minus m over 2 and m over 2, you'll see that there are exactly m integers in this range. But since there's m integers in that range, those m integers form something called a reduced residue system mod m. But that means that if we reduce a, b, c, and d mod m, we can just say that it is congruent to one of the numbers in that reduced residue system. And so that's why we can choose something between minus m over 2 and plus m over 2. That's kind of how that goes there. Okay, well, what does that tell us? That tells us that x squared plus y squared plus z squared plus w squared is going to be equal to or congruent to a squared plus b squared plus c squared plus d squared modulo m. And that's just because arithmetic, quote unquote, works mod m. But now let's observe that this is equal to m times p, meaning that this whole thing is congruent to 0 modulo m, because it's a multiple of m. And then let's also observe the following, and that is that x squared plus y squared plus z squared plus w squared is going to be, in fact, less than m squared. But now, where does that get us? Well, let's actually extend this off a little bit. So the fact that this is congruent to 0 mod m, that means that x squared plus y squared plus z squared plus w squared is a multiple of m. Let's call it k times m. But then if we extend this back and say that this is k times m, that tells us that k is less than m. I think that's pretty clear. If k times m is less than m squared, just dividing both sides by m, you get k is less than m. And now here's where things get goofy, and it's going to involve this like crazy formula, which I think is due to Lagrange, and that is this. Let's take k times m squared times p, and let's write that as k times m times p. But let's observe that is x squared plus y squared plus z squared plus w squared times a squared plus b squared plus c squared plus d squared, right? Because those are our two expressions that we've built over this argument. But now here comes like the crazy formula for this product of two sums of 4 squares. And I'm just going to write this down because it's quite lengthy, but you can check all of the details that this works out just simply by expanding both sides of the equation and seeing that they're both the same. So our first term is ax plus by plus cz plus dw quantity squared. And then our second term is bx minus ay, and then plus dz, and then minus cw squared. And then let's see, our third term is going to be cx minus dy minus az, and then finally plus bw squared. And then our last term looks like this: dx plus cy, and then minus bz, and then minus aw squared. So anyway, if you take a product of two sums of four squares, you can express it as a sum of four squares this way. That actually allows us to eventually extend our result, where we're writing every prime as a sum of four squares, to writing every single natural number as a sum of four squares, which is interesting in itself, although, you know, like we've set up here, we're looking at these Lipschitz integrals for what it's worth. Okay, nice. Now, what do I want to do from here? Well, let's observe that A and X are congruent mod M, B and Y are congruent mod M, and C and W are congruent mod M. So that means that when we were to multiply them together, this is congruent to A squared plus B squared plus C squared plus D squared mod M. But that was congruent to 0 mod M by this result right here, making this a multiple of M. So I'm maybe going to write this as capital A times M. And then via a similar argument, a parallel argument, if you will, you can see that this object right here is going to be a multiple of M as well. I can write that as B times M. This object right here, I can write as C times M, that's a multiple of M. And then this object right here, I can write as a multiple of M, that's D times M. And again, that simply follows from these congruences right here using maybe different little calculations. So notice B times X is going to be the same thing as A times B. A times Y is the same thing as A times B also. So these things cancel out mod M, and then the other two will also cancel out mod M. So anyway, all of those are a multiple of M. But now what we can do is notice that these are all being squared. So what we actually have over here on the right-hand side of the equation is an M squared times capital A squared plus capital B squared plus capital C squared plus capital D squared. Now we can cancel the M squares from both sides of the equation, and we have these capital A, B, C, D squared sums being equal to K times P. But observe that K is less than M. But look, we've just expressed a multiple of P smaller than our minimum multiple of P as a sum of four squares. So that gives us a new contradiction. And that, well, contradicts this minimality of M, and I guess maybe I should have put like M bigger than or equal to 3 in this condition, meaning that M is actually equal to 1. That's the minimum value. But if M equals 1 is the minimum value, that means the prime itself can be written as the sum of four squares. Which means we could go down here to our prime P, which is an odd prime, and then express it as the sum of four squares, A squared plus C squared plus D squared. And then we could factor that using our quaternionic factorization. So we've got this A plus BI plus CJ plus DK, and then the conjugate of that. So A minus BI minus CJ minus DK. And we've got this factorization of P into these irreducibles. And that works for every prime in the normal integers. Now, maybe we'll close this video off with, well, what is actually irreducible inside of these Lipschitz integrals? And then maybe I'll leave it as a semi-open question for you. Are any of these irreducibles also prime? So now for the question of, well, what is irreducible in L? Well, it turns out that everything of the form A plus BI plus CJ plus DK, where A squared plus B squared plus D squared is a normal prime inside of the integers, that is irreducible. And I don't think the proof of this is super hard. Maybe a sketch of the beginning would be something like this. So let's suppose that we have a plus bi plus cj plus dk with a squared plus b squared plus c squared plus d squared equals a prime. And then we could try to factor this. Perhaps it would factor something like capital A plus capital BI plus capital CJ plus capital DK, and then X plus YI plus ZJ plus WK. So that would be our factorization of this thing which we're saying is irreducible. So if it factors and it's irreducible, then, well, one of those has to be a so-called unit. It has to be like have a multiplicative inverse. But now what we'll do is do the norm of both sides. So in other words, what we'll do is multiply both sides by its quaternionic conjugate. But that'll leave us with this a squared plus b squared plus c squared plus d squared equals p on the left-hand side. And then on the right-hand side, we'll have capital A squared, b squared, c squared, and d squared. And then capital X squared, Y squared, Z squared, and W squared. But like, look at what we've got here. Now we've got a factorization within the integers. But if we've got a factorization within the integers, that means one of these has to be P and the other one has to be 1. Now, it doesn't really matter which one, so we could just relabel so that this one is P. But then that means that this thing over here is invertible. Now you can write down the inverse if you want to. I don't think that's too hard. But if the only way to factor this thing is via something that is invertible, that means that these things differ by a unit, which means it's really the same irreducible element here. Okay, so anyway, that's like a hand-wavy thing about why the irreducibles in L2 can be categorized this way. Now, maybe I'll leave it as a question that I don't really know the answer to. It's probably known, I just didn't look too hard to find it. And that would be, what are the primes in the Lipschitz integers? So not the irreducibles, but the actual primes. So maybe if you know the answer to this, post it in the comments. And that's a good place to stop.